To observe the building blocks of light, we start with an evacuated glass tube. Inside this vacuum, there are no air molecules to obstruct the movement of charged particles. The setup contains two metal plates, an emitter and a collector, wired into an external circuit, separated by a gap. When light enters and strikes the emitter, it releases negatively charged particles that travel across the vacuum to the collector plate. We detect this movement using a microammeter. This sensitive instrument measures the resulting flow of electric current as the particles complete the circuit. For our experiment, we keep the color of the light and the battery voltage constant. This voltage creates an electric field, determining the speed and energy of the arriving particles. With the energy of the particles stabilized, we can observe a single variable, the intensity or brightness of the light source. As the light grows brighter, the ammeter needle surges upward. The relationship between the brightness of the source and the flow of electricity is immediate. This observation identifies a direct physical link between light intensity and electric current. However, describing light as a continuous wave fails to explain why this current starts instantly, even under the dimmest illumination. The explanation requires a look at the atomic surface of the emitter plate. Here, free electrons are held by the metal's positive ions. At this scale, intensity represents the density of individual light packets, called photons, bombarding the metal every second. Albert Einstein proposed that light interacts with matter as these discrete units of energy. Each photon carries a specific amount of energy determined by its frequency, or color. This creates a one-to-one interaction. One photon strikes one electron. If the photon provides enough energy, the electron is liberated from the metal surface. Doubling the number of photons hitting the plate per second results in twice as many electrons being released. This increased volume of electrons flowing across the vacuum is what we measure as higher photoelectric current on our ammeter. Because this is a direct collision between single particles, the emission happens without any time lag. The electron absorbs the necessary energy in a billionth of a second or less. The photoelectric current effectively counts the number of photons arriving at the plate. This makes the entire apparatus a precision tool for measuring the stream of light particles. Physicists map these results by placing the intensity of light on the horizontal axis and the photoelectric current on the vertical axis. When we plot the data, the points align in a straight path from the origin. As one value doubles, the other follows exactly. This line confirms that photoelectric current is directly proportional to the intensity of the incident radiation. This linear rise only occurs if the incident light reaches a minimum energy level, known as the threshold frequency. Below this frequency, the individual photons lack the energy to eject an electron, so no current flows, regardless of how bright the light is. Once that threshold is cleared, we observe that increasing the intensity creates more electrons, but it does not make them move faster. We know this because the same negative voltage is required to stop the current, no matter how bright the light becomes. The maximum kinetic energy, the top speed of the most energetic electrons, remains constant for a given frequency. Only the total number of particles participating in the current increases. Figure 11.2 provides the evidence that light consists of discrete particles. In this stream, a higher intensity simply means a greater number of individual packets are arriving every second.